let me just go through the thought process for number 8 on the particle kinematics practice problems. Okay, so number 8, and the idea is, well, the problem is a child's riding on a carousel. And the radius from the center of the carousel to the child is 2 meters. At a given instant, the angular speed is 2.5 radians per second. And it's slowing down with an angular acceleration of 9.5 radians per second squared. And it walks you through a few of these things with the way the questions are asked. So part A, it says draw a picture from above with the z-axis pointing out of the page and the child on the right side of the circle. So from above, the carousel looks like this. Here's the center. Here's the child. And the z-axis is coming out towards us. I'm going to put the x-axis this way. If the z-axis is coming out, what direction does the y-axis have to point? Up, because of the right-hand rule requirements. And then it asks for angular velocity and angular acceleration vectors. Okay. This problem, it doesn't say anything about which way the carousel's rotating. So that means either one of those, so it can go 2 directions, right? I mean, a functioning carousel can rotate 2 directions, this way or that way. Bad carousels can do a lot more stuff. But we're going to assume that this does what a carousel is designed to do. So positive rotation is counterclockwise. Let's do it that way. I think that's the way I did it. Well, actually, since that's the way I did it in the solutions, let's do it the other way. So let's assume that the rotation direction is this way at that instant. Okay. Okay, so if it's rotating this direction and the angular speed is 2.5 radians per second, what would the angular velocity be? I think that's part B. So it asks, what are the angular velocity and angular acceleration vectors at that instant? Well, I guess first, what components are going to be non-zero for the angular velocity? Right, remember that the direction of an angular velocity vector is, you can think of it as like the axis of rotation, okay? And so if this is rotating this way, the axis of rotation is parallel to z. And then we have to think about, is it plus or minus z? That has to do with the right-hand rule. If it's rotating this way, then the angular velocity vector is in the negative z direction into the page. So the angular velocity is 0, 0, negative 2.5 radians per second. Okay, and now what about the angular acceleration? What do we know about that? Do we know anything that can tell us? So we know for circular motion, angular velocity and angular acceleration are parallel. That has to be the case if it's moving circularly in, you know, like in a plane. That's right. If they're slowing down, in circular motion, that means that the angular acceleration and the angular velocity are in opposite directions. So then the angular acceleration has to be equal to 0, 0, positive 9.5 radians per second squared. Yep. Yeah. So if you think of the rotation at any instant as being around an axis, then the angular velocity is always parallel to that axis. Okay. So first of all, it's rotating about the z-axis. Like you can imagine this being a wheel with the z-axis being, you know, the axle, and it spins around that way. So that pins you down to two directions, right? But it still could be either into the page or out of the page. And then the right-hand rule determines which one of those. So we know that it's parallel to z, and now the right-hand rule says it's negative z. Okay, so that's part B. And now, now we just have to use those two circular motion kinematic equations that I gave. Part C says what's the velocity vector of the child. I'll call the child P because his name's Pete. Call this C for center. So the velocity of Pete is omega cross r, which is 0, 0, negative 2.5, crossed with, what's the r vector? Yep, 2, 0, 0. And so you get an answer of 0, negative 5 meters per second, 0. I think in my solution I have it as 0, positive 5, 0, probably because, what? Because it's going the other way, yep. So you're representing a vector going from the center of the rotation to the object that you care about. That's right. Then if the object was up top, it would be 0, 2, 0, yeah. And if it wasn't anywhere near the edge, you know, even though this object has a radius of 2 meters, you could be looking at a point that isn't all the way at the edge. So then in this case, this would be like 0, negative 0.750 would be r. Well, then you just have to use cosine and sine to come up with, you'd have to know the angle or something about it. Okay, so now let's do the acceleration. So we want to know the acceleration of p. So we're going to use the equation all ripe watermelons will rot. And remember, the order does matter, despite what you may have heard in the past somewhere. Okay, so, well, before I solve this, what would we expect from the acceleration? I mean, roughly, we can't come up with numbers or an exact direction, but what do we expect? Remember, the acceleration in a circular motion is broken up into a tangential component and a centripetal component. The centripetal is the easy one. That doesn't depend on direction or anything. That's just always pointing towards the center. So there's going to be some component of the acceleration going from P towards C, right? Then the other component is tangential, and that depends on what kind of acceleration is happening, what's the direction of motion. So what's happening here is the velocity is down, right? It's slowing down. So that means the tangential component of the acceleration has to be opposite the velocity vector. Okay, so we're going to have one component up, that's the tangential component, and one component toward the center, that's the centripetal component. And so the vector is going to be somewhere in the second quadrant, you know, like in this direction somewhere. Okay. The angular acceleration vector is 0, 0, positive 9.5. The r vector is 2, 0, 0. Angular velocity is 0, 0, negative 2.5. And then 2, 0, 0. This, okay, this one, is this the tangential or the centripetal component? That is the opposite of the right answer, the exact opposite. So this is the tangential. Good. And this is the centripetal. I mean, you can remember it because, like in physics, the way you probably wrote this was, or one of the ways you did it was like this, right? That's basically what you have here, but it's a vector form of it. And the tangential was angular acceleration times radius. Okay, so for the tangential component, we have 0, 19 meters per second squared, 0. And does that make sense with what we expected? Yep. And then over here, we have, if you take the cross product here, you have 0, negative 5, 0, I think. And then cross that with 0, 0, negative 2.5. And you get an answer that is what is it? 12.5, yeah. 12.5, 0, 0, negative, right? You should get negative, I think, because this is it's the x component. You have this minus this, so. And if we mathematically got a positive out of this, we know, you should notice that there's something you have to think about. Something went wrong somewhere because we know the centripetal acceleration should point toward the center. okay? And so the total is negative 12.5 meters per second squared, positive 19 meters per second squared, 0. Okay, so that looks something like, that's in a direction something like that. So based on this acceleration of that particle, if you added up all the forces on the particle, what direction would that sum point in? We're about to start talking about kinetics. Okay, so you might be thinking of like adding up like 3 of the forces. But what if there were 7 forces and you added all 7 of them? So don't forget those last 4. It has to be in the same direction, right? Because, right, Newton's law says, I mean, no matter what this m is, it's just a scalar. It can't change directions. And so whatever acceleration you get for this particle, the force has to be in that same direction, not necessarily the same magnitude. All right. Any other questions about practice problems on kinematics? So on a test, most likely I would give you the direction, but in this one you just have to choose a direction and then just be consistent. Probably because I forgot to give the direction. It doesn't matter, right? It does change the answers, but it's just sort of an understanding thing, and that problem works the same either way. Change the vectors. Right. That's right. Yep. Any other questions? Okay. So now we're done with particle kinematics. And so we're moving on to particle kinetics. And remember that all of this, all of the stuff that we've been doing and the stuff that we're going to keep doing right now is all in inertial reference frames. With one kind of gray area, one sort of fuzzy thing. When I introduced those relative motion equations, that's kind of hinting at the start of one type of non-inertial reference frame. Well, like for example, when we did the problem of somebody dropping something in an accelerating car, right? We didn't talk about it as if it was a non-inertial reference frame. But if you think about it, I mean, if you measured all the forces on a cup of coffee, right? And then you measured the acceleration carefully using a camera system that was set up in your car, okay? The only force that you would measure on the cup would be the downward force of gravity. And the acceleration would be in a different direction. So it would look like, based on just based on your measurements in the car and your measurements of the forces, it would look like Newton's second law didn't hold in that case, right? The reason it would look like that is because the same reason as that Jamiroquai video, your frame of reference, your coordinate system is non-inertial, okay? And so when we come back later to those relative motion equations, we're going to be talking about them in terms of like how to use those for non-inertial coordinate systems. All right, so now we're going to, here's what we're going to add to the stuff that we've already talked about. We're going to add force vectors and mass. And later, so now we're talking about particle kinetics, and so we're adding force vectors and mass, but later when we go on to rigid body kinetics, we're going to add moment vectors and moments of inertia. For particles, we don't care about moments and moments of inertia because we don't talk about changes in orientation of particles. We're only concerned with their location, okay? And these are things that have to do with changing the orientation of an object. The equation of motion for particle kinetics is Newton's second law. I'm going to always abbreviate that N2L. And that says that add up all the forces on an object. That's equal to the mass of the object times the acceleration of the object's center of mass. So this F, I'm going to, so this sum of forces really refers to every single force on the object, all internals, all externals. But mathematically, we can treat it as only the externals. And I mentioned this in statics. I'll mention it again when we get to Newton's third law. But that's because all the things that aren't external forces end up canceling out. So the sum of the forces is all the external loads, external forces on the chosen object. M is the mass of the chosen object. And the acceleration of the center of mass is the acceleration of the chosen object's center of mass. When we're talking about particles, that distinction about the center of mass doesn't matter yet because we're assuming that the object only exists at a single point. But when we get to rigid bodies, that distinction is going to be important because if you think of a boomerang flying through the air, the acceleration of one of its tips is different than the acceleration of the center and is different than the acceleration of the other tip, you know? And so Newton's second law only holds for one of those places, and the place where it holds is the center of mass. Okay, so for every time that we use Newton's second law, we have to draw a free body diagram. So So free body diagrams. I'm going to abbreviate that FBD. And these are required in this class for every application of Newton's second law. And when we talk about rigid bodies and talk about the rotational version of Newton's second law, these will be required whenever we're using the rotational equation too. What if my requirements for free body diagrams were like totally different than they were in statics? That would. Okay, so here are the requirements. They're not. It's the same as statics. So first, you need a closed outline of the chosen object. Yeah, it doesn't have to be drawn to scale. But yeah, I mean, for a particle, I suppose just, what do I do? I mean, so on a particle, where forces act doesn't matter. You can either just draw it as a circle, or you can draw the shape, but it doesn't matter where you put the forces. But the closed outline thing means that if you're drawing the outline of a person with bad splay footing or whatever they call that, you don't, pigeon-toed, yeah, that's right. Okay, you don't have to draw the fingers, but that's a closed outline, okay? It's clear about, now if I drew like a vector, a force vector acting on one of these points, it would be clear on what surface it was acting. This is not a closed outline. And the reason that this causes trouble is because you don't know, like, since there's no line showing what the outer surface is, you don't know if this includes the top of the foot but not the bottom of the foot, or you don't know if the grass is included in here. You know, he's standing in grass, by the way. And so this closed outline thing is important just for being clear about what forces are internal and what forces are external, okay? And this outline should have no internal details. And no external objects should be drawn. So if you're doing a free body diagram of a car, it should be like that. It shouldn't be like that. Okay. And again, it's just all so you can be really clear about what are the external forces acting on this object. Like in this free body diagram, or in this picture, you can see like the boundary on this wheel. You know that a force that the ground applies to the wheel is acting on the surface of this free body diagram, and so that needs to be included. Here, the fact that you draw the ground in here kind of obscures that. Is the ground included in this free body? So are we only concerned, so say that this is, blacktop and underneath is concrete, okay? So do we want to include the force that the blacktop is applying to the wheel? Or is the blacktop also part of our chosen object and we want to include the force that the concrete applies to the blacktop? Because those are two different forces, you know? And so that's why you don't want to draw any external features or anything. And then draw all external forces and later couples applied to the chosen object. Okay, so there are two ways to draw forces and couples, and it depends on what you know about them. So first, if the direction of the force is known, then draw an arrow in that direction and associate that arrow with a scalar value. For example, if you know the force is acting in that direction, then draw the arrow that way and associate it with, in this case, it's a variable, an unknown value. It's just r. It's not the vector r. It doesn't have a vector symbol over it. Okay? And the reason to do that is because if you know the direction, you can represent a force vector, even if you don't know the magnitude, with a single unknown value, a single variable. Okay? And we don't want to put in any variables we don't need to. And so if you can represent a force vector with a single variable instead of representing it with two unknown component variables, you're better off this way. Okay. Second, if the direction is unknown, draw a little, like a coordinate axis, coordinate axes, and associate it with a vector value. So, for example, if you don't know anything about the direction, then you could represent the force like this. Or a lot of times you see people write it like this, just, you know, pointing the other way, means the same thing. Yep. Yeah, we just don't know what the direction is. That's the distinction between these two. So, like, are we given the direction, like something in the problem says 30 degrees above horizontal or something? Or is finding the direction part of the things that we need to figure out? Okay, so this is something important to keep in mind as problems get more complicated. How do we know that we've accounted for every force acting on an object? every external force on an object. Well, just remind yourself that in this class, external forces only arise in two ways. The first is the weight, and pretty much everything, well, yeah, I think everything that we're going to deal with is going to have some mass, so there's going to be a weight force acting on it. And the only other type is contact with outside objects at the object boundary. By the way, there are other, these aren't the only kind of forces that can be applied. Weight is known as a kind of body force. That's a force that's applied to all the material in the body. It's not just like applied at a single location. Like some examples of other body forces would be magnetic fields acting on something, or electric fields. But we're not going to be talking about stuff like that. So for us, the only body force is the weight. And then contact with outside objects is called tractions. We, in this class, yes, we are always going to, you can always treat the weight as a point force. And remember that you can always treat the weight as a point force, or any distributed load as a point force, once you've chosen what to isolate. So even when we did internal loads, once we chose what to isolate, what our cut was, then we could treat it as a point force. And in this class, we're not going to do any cuts or anything. So as soon as we've chosen the object, we've already chosen, what to isolate. Okay, so these are called tractions. These are sort of the body force and tractions thing. That's like, that's just to help you sound smart. That's like, you learn those expressions in grad school, so you sound like really extra smart if you talk about these and those, like, isn't that just one type of body force that could be applied to this object? Like instant, like, I'm going to keep, I'm going to keep an eye on that guy. That guy's smart, Not for, that won't work for me because I just told you this, but like in your next classes. Okay, so here's an example. So let's say that there's this truck stuck in the mud. And a guy's trying to push it out. Yeah, it's a really little truck. Okay, so he's trying to push it out, and there's a pig inside, in the back, not inside. No, the pig is just sitting in the, he doesn't get to go in the cab. He's a pig. Let's see. There we go. Now it looks like a pig. Okay. And on the back of the pig is an ostrich or some kind of thing. I don't know. That's not an ostrich, I don't think. Maybe a crane or something. And I don't know, like the EPA is trying to keep this guy from pushing his truck out by tethering him to a helicopter. Okay. Okay, so that's pretty much what's going on. Okay, so draw a free body diagram of the truck. Truck. And then draw a free body diagram of the pig. All right, so for part A, so in a problem like this with a million things going on, just glancing at it can make you get sort of short-circuited or whatever because there's just too much going on. So just remember that you can go through this systematically, So we want a free body diagram of the truck. So draw a closed outline of what we want to isolate. Okay, so there's the truck. And now just think about what loads, what forces are applied to this object. Well, we know there's a weight force. So I'll call that mass of the truck times G. And now we're just mentally going to go around the boundary. The only other types of forces are contact forces. So we can just go around the boundary and look for where something else is touching. Okay, so here there's a force. Depending on whether friction is important here, you might know the direction, it might not. I'll just do all of these as if we don't know any directions. So I'm going to call this the force applied to the truck by the road. And then here there's contact. This is force on the truck by the mud. Here there's contact. This is force on the truck by the person. Oh, I'm going to change that to driver. Yeah, because we'll get into trouble. And then here, there's contact. That's the force on the truck by the pig. Okay. So what about the force that the helicopter is applying to the driver, or the force that the crane's applying to the pig? Those don't come into it because they're not directly applying a force to the surface of the object, to the boundary of the object. The forces that they apply, we'll see when we do complicated problems, they will come into the calculations, but they won't come into it through Newton's second law for the truck. They'll come into it through Newton's second law for the other objects. Okay, so now the pig. That pig looks so scared. Okay, so there's the boundary. You don't have to be that careful with the boundaries. And what forces are acting? There's the weight force. So the mass of the pig times gravity. And then there is contact force. That's the force on the pig by the truck. It's really spread out over both feet, but I'm just going to lump it all in with one here. In some problems that makes sense, in some it doesn't. Maybe the pig's on a skateboard or something. Then it just is at one place. And then where else on the boundary is there a contact? Yep. So there's the force on the pig by the crane. Okay. And so you look at this thing and your first glance says, there's no way I'm going to be able to sort all this out. There's too much going on. But if you just think, apply the weight force, then look for contact, it isn't really too hard to figure out. Yep. Subscripts. Yep, I'm going to talk about that coming up. Yep. Right now, in fact. Would you like to introduce the topic? Anybody care to do this lecture? Anyone feel like they know it well enough from statics 2 weeks ago? Okay, so before I go into that, any other questions about free body diagrams? Okay, so the next thing I want to talk about is the subscript notation. And the subscript notation applies only for force vectors and couple vectors when we get to that. And this vector thing is key. If you use the subscript notation for forces with known directions, if you use it for scalar variables, half the time it's going to mess up your signs. I mean, not exactly half, but somewhere in that ballpark. And the reason for that is the relationship between this subscript notation and how we deal with Newton's third law. Okay, so the subscript notation says the force vector FAB is the force vector applied to body A by body B. So if I redid that last example, the free body diagram of the truck would have the force vector on the truck by the road. Here it would have the force vector on the truck by the mud. Here the force vector on the truck by the driver. And here the force on the truck by the pig. And part B, the pig, would have the force on the pig by the truck. Oh, and I forgot the weight. And the pig also has weight, M pig G. And then standing on the pig, the force on the pig by the, what was that, the crane? Okay, and the benefit of this is that it makes it really easy to spot cases where we're dealing with a force vector on A by B and another force vector in a different set of equations on B by A. That's when Newton's third law applies. You can see it here in this and this. And so this is where we're going to end up using Newton's third law. So if we had like a typical statics problem where we had a structure connected by pin joints at the top, pin joints to the ground, say this is member 1 and this is member 2. The free body diagram for member 1 has the force on 1 by the ground, the weight force, and up here the force on body 1 by body 2. And this one has the force vector F on 2 by the ground, the weight force M2G, and then up here you have the force on body 2 by body 1. And these two again are going to be the place where Newton's third law comes in. Any questions about that? Okay. So Newton's third law I'm going to always write it just N3L. And this is always a way to reduce the number of variables that you have in a set of equations to the minimum that's required. In words, Newton's third law is that every action has an equal and opposite reaction. But that wording is, it's easy to misunderstand that or use it wrong. Mathematically, all it says is the force on A by B is equal to negative force on B by A. When a force is in a known direction, and is represented by a scalar variable, you should think do these two forces No, erase that. Do these two forces, if these forces had been full unknown vectors, would they just have opposite subscripts? Okay, so I think that's a good way to think about like whether two forces where you know the direction are candidates for using Newton's third law. If so, change the direction of the arrow, or, you know, switch, make the direction opposite. And keep the same scalar variable. Okay. Any questions about that? So let's take a break and come back at 2:13, and I'll do a couple of examples with sort of complicated systems where we'll work through all this stuff.